Okay, let me wait for a few minutes. Let me share the screen. I will wait for a few minutes to few students to join in this session, and then I will start. Okay, we can start because I have to revisit few problems from the previous sessions. So let's start without a further ado. So okay, and so this is the week 4 assignment sessions where we will discuss about the assignment problems that are mainly based on the lectures of week 4. And basically in this session at first we will complete few problems that few students have has difficulties to tackle. So we'll first solve those problems, and then again we'll start the problems for week 4. So this is my Google on the website for me. Do check my website, and this is the YouTube channel where you will get all the assignment sessions. So if you like the videos and the content, then you can subscribe to my channel. Okay, so as I have said earlier, so today we will first talk about few problems that few students have difficulties to understand. So this problem says 1 mole of an ideal monoatomic gas at initial temperature of 300 Kelvin expands reversibly and adiabatically. So we have to first do these two things, reversibly and adiabatically. And from volume 5 decimeter cube to 10 decimeter cube, and the problem is calculate the work done in this process. So we have one clue, which is adiabatic. That means Q is 0. So as from the first law of thermodynamics, we know that du is Q plus W, or in other words we can write in this fashions also, dq plus dw. This cut means these are not exact differentials. So if you have this dq equal to 0 for adiabatic process, then du is equal to dw, and du, as you know, you can expand it like this: del u del t at constant v into dt. Now here, since this is ideal gas, this u is not a function of any other things like p or v, so we can write it in this fashion only, and this is cv dt, where cv is equal to del u dt at constant v. Now to calculate the energy, the work done, we have to what we know that this for adiabatic process, adiabatic process, PV gamma is equal to constant, and for ideal gas PV is equal to RT for 1 mole gas, so we can write P as RT by V times V to the power gamma is constant. Then we can write T V gamma minus 1 is another constant, let's say K. Sorry, this. Also we can write as in terms of this kind of expression. Let's see what would be the work done. So as we know, this dw is minus pdv. So w in the whole process will be v1 to v2 minus pdv. But for adiabatic reversible adiabatic process, we can also get we know these expressions, right? So let's say this is k prime and this is k, so we can write as minus of v1 to v2 k by v to the power gamma dv, and if you do the integration, then it will be v to the power minus 1 minus gamma plus 1 to v1 to v2 with some k and some constant, that would be 1 minus gamma, and we can write it as 1 by gamma minus 1. What is this k? This k will be similar of this PV gamma, so this will be P1 V1 gamma, sorry, P2 V2 gamma by P1 V1 gamma, like this. So let's do this in a good way. So this will be if you write in this fashion, then Okay, I have to write it in this 1 by gamma minus 1, there will be k, 1 will be v2 1 minus, there will be gamma minus 1, there will be minus of that, minus v1 gamma minus 1, and we can write k as p1 v1 gamma is equal to p2 v2 gamma. And if you replace this, then we can write as k means for first thing it will be p1 p2 v2 gamma, then it will be gamma and minus 1, so there will be 1 left, so we can write as, sorry, I have done something, this will be gamma minus 1, so there will be 1 minus gamma, so there will be slight mistake. So for first one, this is p2 v2 gamma times v2 1 minus gamma, so there will be 1 gamma left, 1 v2 left, so let me write it in p2 v2 gamma v2 minus gamma plus 1 minus for first thing p1 v1 gamma, so p1 v1 gamma into v1 1 minus gamma by gamma minus 1. So then v1 gamma, v1 1 minus gamma, there will be 1 v1, so p2 v2 minus p1 v1 by gamma minus 1. And here we can also write as we know pv is equal to RT, so R T2 minus T1 by gamma minus 1. Let me add a page to this thing. Insert. Okay. So there we can write as this, and this will be R by gamma minus 1 into T2 minus T1. Also remember, Cp by Cv is equal to gamma, and Cp minus Cv is equal to R. And if you divide this expression by Cv, this expression, then this will be Cp by Cv minus 1 is equal to R by Cv. Then we can get gamma minus 1 is equal to R by Cv. And we can write Cv is equal to R by gamma minus 1. Then the expression of W or dW becomes R by gamma minus 1 T2 minus T1 is equal to Cv of T2 minus T1. So you can, both these expressions are right. So where this Cv will be there, you can. Now in our problem, there is ideal monoatomic gas. So for monoatomic gas, let's monoatomic gas, gamma is 5 by 3. So if gamma is 5 by 3 and we know R 8.314 joule per mole Kelvin, so we have to find T2 and T1. T1 is given, what is T1? 300 Kelvin, that is 300 Kelvin. So how can we find T2? T2, for T2 we have to get help from this equation. So to find T2 we have to write T2 V2 gamma minus 1, I guess. Gamma minus 1 is equal to T1 V1 gamma minus 1. That actually imply T2 is equal to T1 times V1 by V2 into gamma minus 1. Now if you do the calculations, then T2 will be 300, and what is V2? V2 is 10 decimeter cube and V1 is 5 decimeter cube. So their ratio will be V1 by V2, that will be half. Gamma minus 1 means 5 by 3 minus 2 minus 1, sorry, that will be 300 times half 2 by 3. Now you can see this T2 will be less. What will be this T2? This T2 will be 180, I have calculated it, 9. Sorry for the, and this will be 188.988 Kelvin. And if you put all the informations in the equations, then W, as we know, will be R, which is 8.314 by gamma minus 1, means 5 by 3 minus 1, that will be 2 by 3 in 188.988 minus 300. And if you do the calculations, this will be nearly minus 1396.71 joule. So this will be the correct answer. This one. So this will be the correct answer. So is my problem is understand. So this is kind of a two-step process. First, what we have done is, let me just stop presenting and present again, so that okay. So where in the first thing, what we have done, we have first made the premise that what is this adiabatic process mean. This process actually means that the net heat exchange with the system is 0. So that will make that Q equal to 0. And from first law of thermodynamics, we know that change in internal energy is happened from two fronts. One is change in heat, and what is the amount of work done. Now from that perspective, we can write du is equal to Q plus W, or in other notation it will be del Q dQ del W. So since dQ is 0, so that will del U equal to del W. So the internal change in the internal energy is the amount of work done. Now for ideal gas, internal energy is only function of temperature. From that we can write del U as del U del T. What is the change in the temperature with respect to what is the change of internal energy with respect to change in temperature, and the change of temperature, that is CBDT. From that, if we integrate this amount from T1 to T2, we can get CBDT. And if you get the integration of dt from T1 to T2, that will give you CV times T2 minus T1. Now from this perspective, from P and V, if you given the P and V, how can you calculate it? For that, we know that work done is minus P dV, and V change is V1 from V2. And from adiabatic process we also know that PV to the power gamma is constant, and since it is ideal gas, so there will be PV is equal to RT, ideal gas equations, and if you substitute the form of P from this equation, that will give us this T V to the power gamma minus 1 is equal to some constant we have kept is a key prime. Now for this total work done in this process can be calculated by substituting P as K is a constant, K by V to the power gamma, and if you do the integration, then from the integration we can get the expression K by gamma minus 1 times V2 to the power 1 minus gamma minus V1 1 minus gamma. Now K, since a constant, it is P1 V1 to the power gamma is equal to P2 V to the power gamma, and we have substituted that K, and by simplifying the expression we get P2 V2 minus P1 V1 by gamma minus 1. Now we know P2 V2 is equal to RT2 and P1 V1 is RT1, then we just substitute it, and after that we can get R by gamma minus 1 into T2 minus T1. Also Cp by Cv is equal to gamma, and from there we know we can get that Cv is equal to R by gamma minus 1, and from that also we can establish this expression R by gamma, the work done is Cv times T2 minus T1. And after the calculations we have to find the T2, all the things are given and we have found the T2, and then we can get the work done. Now this is a big calculations which is related to this problem, so we will do one by one. Probably what I can do, we can while deriving this whole equations we can stop after completing one part, and then we can summarize all those things and summarize all those things to get the thing. Okay, so the expression the problem is given is except hydrogen and helium, Joule-Thomson coefficient of real gases at ordinary temperatures and low or moderate pressures is something positive, negative or zero. Now to do this thing we have to first know what is Joule-Thomson coefficient. At first we know what is this thing. This is enthalpy, and enthalpy is defined as function of P and T. Now we can write the change in enthalpy TH as del H del T at constant pressure dt plus del H del P at constant T dP. Now for this Joule-Thomson effect we know dH Joule-Thomson is 0. So we can get del H del T at P equal to dt is equal to minus del H del P T dP. Now Joule-Thomson coefficient GT is defined as del T del P at constant, because this is for Joule-Thomson for Joule-Thomson effect the enthalpy doesn't change, so it's a isenthalpic process. So what does this call? This call isenthalpic isenthalpic process. So what we can do after this, like bringing this dp, let's keep pointer options, so laser pointer. So we can bring this dp to this end, and we can move this del h del t at constant p to this end. So now we can write as minus del h del t at constant p 1 by, obviously because we are bringing this one, in del h del p at constant t. Now we all know that Cp is del h del t at constant p. So now we can write that mu jt is equal to del t del p at constant h is equal to minus 1 by Cp and del h del p constant t. So this thing we should know, this thing a constant. I just derived it for your thing. So let's just revisit what we have just learned. So we since enthalpy is a function of pressure and thermodynamic variables, which is pressure and temperature, we can expand that with respect to those variables, and after expanding that we can get del h del t at constant pressure dt plus del h del p at constant temperature dp, and then we can for Joule-Thomson effect we know that is an isenthalpic process, the change in enthalpy is 0, so we can play around those expressions, and we can get the expression as mu jt is equal to del t del p at constant h is equal to minus 1 by del h del t at constant p times del h del p t. Now Cp, which is a one kind of a heat capacity at constant pressure, that is del h del t at constant p, then we can get the expression. Let's just go into the derivation. Now what we know is H is U plus Pb. See this thing carefully because it will be helpful for the few problems that come next. Del H will be del U plus P del V plus V del P. Okay. Now these two things, del U, P del V, we know this is T del S or TDS, or let's TDS, or if you write in VDP. Now if you write in this differential, this will be of del, and if you take the differentiation with respect to P, then it becomes del H del P, let's take it constant temperature at T is equal to T del S del P at constant T plus V, because this is dP with respect to P, the differentiation, so it will be 1. Now we will use the Maxwell relations. I want to give you just one mnemonic diagram, SPTV, and this goes as follows. If you take the derivative in this region, or del S del P and del V del T, they will be kind of a negative, and if you take this derivative in this direction, so this direction is positive, this direction is negative. Positive and negative. So del H del P at constant T will be minus del V del T at constant P. That is understood? So this is a mnemonic kind of a thing. So remember this. This will actually save most of your time while calculating the thermodynamic variables, some relations. So del S del P at constant T. So now del S del P means in this direction. So there will be a negative del V del T at constant P. So now we will substitute it here, minus T dV dt at constant P plus V. So now if we write the expression of mu Jt, what is the Joule-Thomson coefficient? So we can write now as, there will be minus, one minus will be there. So minus 1 by Cp is equal to minus T del V del T at constant P at V. And if you just play around the sign, Cp minus V plus T dV del T at constant P. So this is the final expression. Okay, let me add few pages so that I can call. Okay. So far so good, everything is right. Now for the completeness I will just do the for ideal gas. So for ideal gas, what we know is PV is equal to RT. That actually, sorry. So PV is equal to RT. Now if you want to know, the NV will be RT by P, and if you want to know del V del T at constant P, then there will be R by P. And if you substitute in the expression of mu Jt, which is 1 by Cp T dV dt at constant P minus V, then it becomes 1 by Cp T and dV dt is R by P, so RT by P minus P. Now this RT by P, remember this is V, so this will be V, so V cancel out, so it will be 0. So for Joule-Thomson effect for ideal gas, there will be no effect because mu Jt is always 0, so there will be no heating or cooling. Now for ideal gas, because this hydrogen and all those gas are ideal, for them this is quite different. So what are the ideal gas equation? This is actually P plus, we will write for 1 mole gas 1 by V square times V minus P is equal to RT. So if we play around those things, we can write PV, let's do this, minus PB plus A by V minus A B by V square equal to RT. Now rearranging them, we can get PV is equal to RT, okay, plus PB minus AV plus AB by V square. Now we will do one trick is by replacing this V by RTB by P. Because we can do this, because this A and B, these are very less than V, very less than V. So if you replace this by this V equal to RT by P, that will not change as much, because anyway we are taking into consideration the the change of the interactions. We are just doing by substituting the V according to ideal in this expression to get to know what are the changes. So we can do this because this is some kind of approximation. Let's say you are talking about 22.2 liter volume with respect to 0.0001 volume on liter volume. So you can take that, you can neglect that. So if you do that, then you can write, let's write it V RT by P, P B, so B will be cancel out, minus A by V. So A by V means V will be RT by P, RT by P, and this P will be there, so RT by P into P plus AB by RT by P square into P. So this will actually give you RT by P, RT by P plus B minus A by. So actually to do this, why we are doing this, because you can ask, so we want to know that what is the change of volume with respect to temperature. So far in this thing, this R and T, there will be only one thing. So we actually, if you do that del V del T with respect to this, and if you get this, then this will be cancel out. So but this will be a complicated equation because this will be hi. Hello. Hello. Hi, Saraj. Response. Okay, so we are actually deriving the Joule-Thomson coefficient for ideal for real gases. So if you do this thing, then we can get RT by P B minus RT plus AB by ABP by R square T square. Now we have to find that del V del T at constant P. Now if we do this, then there will be, for first term, this is will be R by P, so this will be R by P. For this thing, this will be A by RT square, and Okay, so this was our expression. Okay, del v del t. Okay, so this is r by p, a by b not, this is not b, this will be r t square minus 2ab p by r square t cube. Now we have to do the del v t dv dt at into p. So for that we have to times this, we have to multiply with t. So this will be rt p plus a by rt minus 2ab p by r square t square. Okay, so now if we substitute in this expression mu jt, this is 1 by cp t dv dt times this will give you rt by p plus a by rt minus 2abp by r square t square. Now this r by p, actually this r by p can be written in terms of this v also, because this is yeah, here we can write in terms of this. So let's write, this will come in a nice expression, so let's do that first. So v is equal to rt by p plus b minus a by rt plus a by r square t square p. So if you write r by p, then you can write v minus b by t minus, if you take this one, then you will plus a by rt square minus abp by r square t cube. So why this is important? This is how is this done? So this b, everything will be in this side, so b minus b, this there will be a by rt, there will be minus ab by r square t square, and if you divide with respect divide by t, then there will be v minus b by t, a by r t square minus ab by r square t cube. Now substitute this r by p here, you can get the full expression here. So there will be one, if you times t, then it will be a by rt, this will cancel out, and there will be one, so this a by rt and this a by rt will add up, and we can write in a good fashion. So what do I mean by this? This rt by p, so if you times this there will be v minus b, and this b, this will cancel out, so there will be minus a by rt, abp by r square t square, and there will be a by rt, so this a rt will actually can probably they will add up. Let's write them. Okay, let's add one page. Okay. Okay. So let me write once again. Del V del T at constant P is equal to R by P. Let's add this T. RT by P plus A by RT minus 2A BP by R square T square. And this, from this expression, so RT, this expression, from this expression, R by P is equal to P minus B by T, A by RT square minus ABP by R square T cube. We can times T, then it will be P minus B and all those stuff. Let's write them in different fashion. So one by one, if you write it, then we can get RT by P is equal to P minus B plus A by RT minus ABP by R square T square. Now if you just put this expression here, what to become is T dV dt at constant P will be V minus B times 2A RT minus 3ABP by R square T square. Now you can get the coefficient is 1 by Cp dV dt constant pressure minus V. So this V will cancel out and you can write directly 1 by Cp as 2A by RT minus 3ABP by R square T square minus B. And this is the expression. Okay. Now when the pressure, in the question is the pressure was ordinary, temperature was ordinary and there was low pressure. So for this thing, low pressure and temperature at room, so this P by T is tends to 0. So since this is T square also, so this will, I can drop out. So we can write mu Jt is equal to 1 by Cp and 2A by RT minus P. So there can be three things. First, mu Jt can be less than 0. That will be when 2A RT will be less than B. So when this is negative, mu Jt is negative, we can say that dt is also negative, change in yes, because remember this mu Jt is del T, mu Jt is del T del P at constant H, del T del P at constant H. So this is expansion, so del P is always negative. So if it is negative, then it is, this will be positive. So when mu Jt, the Joule-Thomson coefficient, is negative, the temperature will increase. So it will be heating. So when mu Jt will be positive, means 2A RT is times B, then we can say this dt will be negative, because dp is always positive, always negative, so dp is always negative, is always negative. So but there will be one scenario where 2a will be b. This is called inversion temperature, b by br by 2a, sorry, 2a by rb. This is inversion temperature. Here there will be no effect of the heating or cooling. But the question was, so in that question was the low pressure and high temperature. So for that we can write this thing. So this will be mu gt will be always negative. So this will be sorry, what was the question? Question was the moderate pressure and ordinary temperature. So moderate pressure and ordinary temperature means means 2a by rt is always greater than b, because b is a very small number, so this will be always greater than this expression will be always greater than b, so this will be always positive. But why for not for hydrogen and helium? Let me add one more page, then it will be clear. I can write clearly. Now for hydrogen and helium, for hydrogen and helium, A is very small. A is very small. There 2a by RT actually get less than B even at room temperature, even at room temperature. So there, since that is always less than T, so there will be always so from this expression this mu gt will be negative. So then that will then their mu gt will be negative. So that's why for hydrogen and helium this will be there will be heating even at room temperature. There can be many more expression, but let me stop here because then we will deviate from our discussions. So let's just discuss the thing. Let's just summarize the whole expression thing. So enthalpy is a function of pressure and temperature, so we can expand the enthalpy function in terms of temperature and pressure, and then we can, since it is an isenthalpic process, so dH will be dH, enthalpy change will be 0. We can rearrange this thing, and after that the Joule-Thomson coefficient is described or defined as change of temperature with respect to pressure at constant enthalpy, and which can be written in terms of this, and del H del T at constant pressure is Cp, and then after rearranging we can get mu Jt is minus 1 by Cp del H del P at constant T. Now for ideal gas we know that then del H del P del T we can write as this is TdS, So this is this after writing in differential, you can write as T ds del P del T plus V, and from this mnemonic diagram we can get del S del P at constant T is minus del S del V and minus del V del T at constant P. After substituting, we can get mu J T is 1 by Cp minus V plus T dV dt at constant P. Now for the ideal gas, we know the ideal gas equation Pv is equal to RT. We can get the expression V equal to RT by P, and then after taking the differentiation with respect to T, we can get del V del T at constant P is equal to R by P. And then after substituting this in this expression, we can get RT by P, which is V, then V minus V is 0. So for ideal gas, there will be no heating or cooling because mu Jt, which is the Joule-Thomson coefficient, is always 0. But for the real gas, it is different scenario. Because for Van der Waals gas equation for real gas is like this. So after expanding, we can get this, and then rearranging for V, we can get V equal to RT by P plus V minus A by RT plus ABP by R square T square. Then after taking the differentiation with respect to T at constant P, we can get R by P plus A by RT square minus 2ABP by R square T cube. Then just multiplying T, we can get RT by P and all those things. And again, we can use this RT by P thing in this V, because we can put this RT by P back into here, and putting back into here, we can get this expression RT by B is V minus B plus A by RT minus ABB by R square T square. So putting that in this expression, we can get, so this V minus B will be there, and this A by RT will be added to this, this A by RT will be added to this thing, and this also added to this thing, so this will be this. And after putting all those expression in together, we will get this kind of a expression. And we can get trick scenario. First, we have to neglect this thing because at low pressure and room temperature, this thing is very small, so we can neglect this. So scenario 1, when it is 2A RT by B, 2A by RT is equal to B, there will be no heating or cooling, so this will be inversion temperature. And for this, Joule-Thomson coefficient will be negative when 2A RT is less than B, so this means dt is equal to positive, there will be heating, because dP is always negative, so this del T del P will be negative. And when the Joule-Thomson coefficient positive, means 2A by RT is greater than B, that means del T is negative, so their ratio of del T del P will be positive. But for hydrogen and helium, it is quite different, because the pressure correction term is very small, because these are very small atoms. So then 2A by RT is less than B even at room temperature. So then we can say this mu Jt is less than 0. That means it is negative. That means, let me change with pen. So that means heating, dt greater than 0. Okay, so this is big expression. Let me go to the another problem. So this was the previous problem. It is similar to the previous thing. Only thing is the pressure is here. The pressure is changing. There was in the first problem, it was volume was changing. So we can do this. I can write the expression, because this is a similar thing. So as we know, this is adiabatic. So adiabatic. So work done is R by gamma T2 minus T1. Now we know that for PV gamma is equal to constant and PV equal to RT. Putting this into this will be RT by P by gamma equal to constant that makes P1 minus gamma T gamma equal to constant. So we can get the T2 1 minus gamma T1 gamma is equal to P2 1 minus gamma T2 gamma. So T2 will be T1 times P1 by P2 into 1 minus gamma by gamma, and gamma is equal to 5 by 3. This is a monoatomic gas, so you can get T1 is P1 by P2, so this will be 2 times 1 minus gamma, that will be minus 2 by 5. And if you substitute everything, so there will be 3R by 2, because gamma is 5 by 3, so gamma minus 1 will be 2 by 3. And T2 is we can get T1, so 2 to the power minus 2 by 5 minus 1. There will be one minus because of this, and we can get the expression of, if you substitute it, we can get this T2 will be 393, sorry, is, so if you do the calculations, you can get minus 899 joule. So this will be this expression. Okay, so this is a simple problem, just like the previous problem. So let me start today's problem. These are very small problems. We will do those problems now, and hopefully the Joule-Thomson coefficient problem is understandable to you guys, and this is very important because this is quite comprehensive calculations. So let's just start this problem. This problem says two equations is given. One is PCl3 in liquid phase plus Cl2 gas phase and produces PCl5 dash, and two equations are there. So to tackle this kind of problem is quite simple. So it's just, if you follow closely, let's what we can do this expression. So equation 2 minus 2 times equation 1, if you do this thing, what we can get 2 PS plus 5 Cl2 gas minus 2 PCl3 liquid plus, minus 2 Cl2 gas, which produces, this will negate, so this will be something 0. Now you just do this thing, 2 PS 5 Cl2 2 Cl2 3 Cl2, and if you bring back this thing here, this will be 2 PCl3. Now in this time, what will be the del air H? So because this will be simply same thing, so minus 887 kJ for the equation 1 times minus 2 into this is minus 124 kJ, because this is simply equation 2 minus 2 times equation 1, so their del R H will be also proportional. So from this thing we can write minus 887 plus 248 kilojoule, that becomes 6 minus 639 kilojoule. So this first option will be correct option. Okay, this is pretty simple. So this is just one expression where we have just did this calculations. Okay, so I'm going to the next problem. Any question? No. Okay. So here is given. Okay. Let me go to this. A student is doing an experiment on bomb calorimeter. Since in the experiment del V equal to 0, then which of the following expression gives delta H? What is the change in enthalpy? So you know that H is equal to U plus P V. That makes delta H is delta U plus P delta V plus V delta P. Now yes, change in this expression they said that del V equal to 0. So this will be 0. So this is pretty simple. This will be delta U plus P delta P. Okay, quite simple. So this will be, this expression is correct. Okay. Next, go to the next problem. This problem says a system of ideal gas containing 1 mole is taken from T1V1 to T2V2. Okay, it's T1V1 to T2V2. Then assuming Cv to be constant for this temperature range, del S for this process is given by the equation this. Okay. Okay. So, first of all, what is the first law of thermodynamics says? Del U is Q plus W. Now, Q will be del U minus W. We know that entropy is the change in entropy Ts is Q by T. So this will be del U by T minus W by T. So what is the del U? Change in internal energy del U. This is Cv dt. What is W? dW. P dV. Simple. Right? Now ideal gas means this will be RT by V dV. Right? Now for this thing, what will be the ds? So ds, let's say write del S for internal energy and del S for work done. Two things. One will be del U by del T, so it's Cv dt by T. One will be RT by V T, because there will be T will times dV. So one will be R dV by V. Let's just integrate it and take the expression. So this will be change in entropy delta S will be T1 from T2 Cv dT minus V1 to V2 R dV by V. And if you get this thing, then you just Cv ln T2 by T1 minus R ln. Okay, there will be one minus. One will be minus. So this minus cancel out. So there will be plus ln V2 by Vn. So first one, this option, so CP will not be there, CP will be there, only two options they can be correct. So there will be P2 by Pn, no, V2 by V also. This option is correct. Okay, so just see this problem. If you have any question, I can take it. Okay, take few minutes. Okay, let's continue our discussions. Okay, so the fourth problem says, quite interesting, is for an isochoric process, del S is given by the equation, which equation? Now, for isobaric process, as you know, isochoric process rather, you know that dv is so this dv is 0, means isochoric process. Okay, so w will be minus pdv, so this will be 0. Only entropy change or del S will be from du, which is cv dt by t. Now if you integrate out this change in entropy, delta S will be T1 from T2, Cv dt by T will be Cv ln T2 by T1. So this will be option number 1. So this thing. So it's quite the extension of the previous problem. It's quite easy. So for isochoric process, you know that dV is equal to 0, so minus pdV will be 0, so there will be only due to the change in internal energy, there will be a change in entropy, and that will be Cv ln T2 by T1. Okay, let's go to the next problem. This problem says a system goes from state A to state B by an irreversible path. During the entire process from A to B, the system is isolated. Then it is brought back from B to A following a reversible path. But in this process, it is allowed to exchange heat with the surroundings. Then which of the following equation is true? Okay. So to do this, for irreversible process, this equation, this first law of thermodynamics is always true, right? It is always true. For reversible process, we can write du reversible is dq reversible plus dw. Rather, we can, since we can write it as dq or dt plus dw, what we can write as tds, because we can write entropy in terms of reversible heat in reverse, the heat exchange in the reversible process. Now if we take the so change in internal energy will be same, because internal energy is a state function, so we can write tds plus dw is equal to del q plus dw. Let's say it is irreversible, this is reversible, so we can write as ts is equal to tq in irreversible process by t plus 1 by t dw irreversible minus dw reversible. Okay, now we know that in irreversible process dw irreversible is less than dw reversible. Okay, so from here we can actually write delta S SB minus SA equal greater equal to A to B dqir by T. So this is if we take the mod, and for the okay, so for irreversible process, if it is isolated, so we can write SB minus SA greater than 0. Equal will be equal to 0 when it is reversible. So this third last option is correct for this type of thing. Okay. This is quite simple. So sorry, this will be actual work. This will be actual work. So TQR actual. So in that process, when it is in doesn't change head with the surroundings, it will be 0. So we can write in terms of this. Okay, let's go to this next problem. Next problem says, if two equal quantities of ideal gas are mixed, then del max S is given by the equation. Okay, now to do this, we know that from the previous expressions that since let's say temperature, pressure all are constant, then only delta S will be dW by T. So from here we can write delta S as, so this will be a minus, so minus and minus plus P dV by T for ideal gas. This is RT by V dV V1 by V2. So we can write R ln V2 by V1. Okay, there will be T, this T is to cancel out. So if equal quantity mixed, so then there will be V1 prime and V1 double prime will be V, then V2 will be V1 prime plus V1 prime prime, there will be 2V. So we can write R as ln 2V. So delta S will be R ln V2 by V1 ln of 2V by V, so R ln 2, which can be written as R ln half, because this also can be written as r of ln of 2 to the power minus 1 minus 1. This minus 1 comes outside, and this 2 to the power minus 1 is half. So this is the expression. So the right option will be this one. Okay? Any questions so far? Any question? Okay, wait for a few minutes and then let me check. The video is being recorded. Okay, so this said a Carnot engine has same efficiency between 200 Kelvin and 400 Kelvin and T1 and 1000 Kelvin. Then what is the value of T1? So at first let me give a brief review about Carnot engine. So this is a PV diagram of Carnot engine. There will be a isothermal expansion, then adiabatic process, then adiabatic expansion, followed by a isothermal contraction, compression, and with by. So it starts from this, 1, 2, 3, 4. This is a T1, this is a T2. And the efficiency eta is written as delta W work done and Q input, which can be written as 1. Delta W is Q out or Q in minus Q out by Q in, then 1 minus Q out by Q in. And in the lectures I have shown that this Q out by Q in can be written in terms of T2 by T1. That means Tc by T. This means like cold reservoir temperature, and so this is a cold reservoir, this is a hot reservoir. Now first thing they said that so eta 1 is same as 1 minus T2. They said 200 by 400. The second one says 1 minus T1 by 1000. So if you equate both these two, then we can get 200 by 400, 1 minus T1 by 1000. And then we can get half is equal to T1 by 1000. And we can say that T1 is 500 Kelvin. So the right option will be option C, option A, sorry, first option. 500 Kelvin. Okay. Okay. This problem says if a process involves isothermal transfer of heat, then ds, the change in entropy, is given by which of the following equation? Del S is equal to del Q irreversible by T, because this is not an irreversible process, so we cannot write like this. Del S equal to 0. That we also cannot say because this is not an isolated process, isolated system, so we cannot say like this. Third option, del S equal to del Q del T, that we can think of. Last option is del S equal to del Q reversible by T. This is also not a reversible process, so we cannot write like this. So we can say that option C is more close. So we can say that option C, this is right, because we can always ds is dqi by ti with different processes, so we can write option C is correct option. Now this problem, a gas at 0.2 atm is enclosed in a weightless and frictionless piston, and the cylinder is placed in the surroundings where pressure is 1 atm. Now, in the spontaneous process that occurs isothermally, which of the following statement is true about the entropy change? Now, this is quite interesting. Now, the system and the entropy, if we consider the system and the surroundings both as a combined system, that system is isolated. Okay. Now, the combined system of system and surrounding, the entropy is 0 because this is isolated, no heat exchange. So if system's entropy increases, the surroundings entropy decreases. That one you can say, right? Because if that is an isolated system, total combined system, and their entropy doesn't change, then if entropy of one component of the system, that is one system, the subsystem, is changing or is increasing, then other thing will decrease. Okay, so let's just first comment about the system's entropy. Okay, now for this thing, gas pressure is just 0.2. Okay, so here P1 is 0.2, P2 is 10 probably. I can't say you 1 atm, sorry. P2 is 1 atm. Now if we see it's an ideal gas and this is isothermal, then V1 V2 will be P2 by P1, so that will be 1 by 0.2, so that will be 5. So it is actually a compression. Now we got the expression of entropy delta S is R ln V2 by V1, that is R ln 1 by 5, and it is less than 0. So system entropy decreases. Now from our argument, of combined system plus surrounding, which is isolated, for that d is equal to 0. So surrounding entropy must increase to balance that. So we can say that system entropy of the system decreases and of that of surrounding increases. Okay, so you can follow my argument, right? Why is this happening? Because when we are considering the system of our problem and the surrounding as a grand system, and which is isolated because there is no heat exchange of that combined system, then we can say for our second law of thermodynamics that entropy doesn't change for that combined system. Now in that combined system, we have shown that the system in that combined system, means like the system in our problem, that for that entropy is decreasing. So to balance that out, entropy of the surrounding must increase. Okay, that's the thing. Okay, this problem says in a Carnot refrigerator the coefficient of performance is sun. This is definition. So what is this Carnot refrigerator? Is this is T hot, this is TC, so there will be some amount of heat that we need. So this is, let's say, QC, and we have to need work to send the Q hot. Okay, and this coefficient of performance is actually defined as mod of QC by W, and it is always greater than 1. Okay, because QC is probably always. Okay, because you can but we cannot actually say that because here you can write QC is QH minus QC, right? Then this can be written, because if you just reverse the thing, that will be a okay, no. So QC minus QH, this will be QC minus QH, that will be this thing. So from there we can write. Okay, no, this QH will be QC plus W. So W is QH minus QC. These are the reverse of the, just change in direction of the reverse of the thermal engine or Carnot engine. Okay. Now this also a simple problem. This says if there are n reversible engine working between two temperatures T1 and T2, given that T1 and T2, given that T1 greater than T2, the efficiency of the engine will be. So this is a problem from the definition. So let me write. Carnot engine eta is 1 minus T2 by T1, where T1 greater than T2. That is I hopeful that that is the yes. Okay. So it only depends on the T1 and T2. So actually efficiency will be similar because this is an ideal engine. Efficiency will be same because it only depends on ratio of T1 T2. Okay. Okay. The last problem, sorry, probably this is okay. The last problem, the second last problem, the entropy of a process is given by entropy of a process. So for a process, this should be a reversible, because for irreversible thing we don't know, cannot define the entropy properly. So this will be this thing. Okay, this is also very easy. Now this thing says, is the below constructed engine correct given that T1 greater than T2? Now this thing, what you can say, so there will be some heat, let's say Q2, there will be some heat, this is Q1 and this is some W. So from here you can say that you are doing an unthinkable and unreasonable thing, which is you are sending heat from, which is sending or transmitting heat from cold to hot reservoir, and this is spontaneously, means no work done, because you are also getting some work, that is also perpetual work is also obtained. So this violates second law, probably. So surely this violates the second. Okay, let me start. Okay, so this violates second law, also the Clausius statement. So this thing. So that's the end. So you just I will wait for a few minutes to have some questions, and then I will summarize both things, and then I'll finish this session. Okay, let's start from here, and I'll change the I think you guys should see these derivations, and if you have any question, then we can actually address those things, because these are the most. I will share those slides, and this will be actually this calculation is important to understand. Okay, just see these calculations. If you have any question, you can say me. You can tell me. If you have any, then you can answer those questions. Okay, so since you have no questions, we have quite a few minutes, so we can actually extend few ideas. Here, let me add a slide then. Okay, yeah. Okay, so as I have said earlier that while doing this calculating this Joule-Thomson coefficient, we can actually what we have did, we actually neglect 3abp r square t square. If you see here, we actually neglect this term. We actually neglected this term. Now if you let's say you want to you don't want to neglect this term, then what happens, and you put it here, and you want to keep this thing, then what you can get, and minima maxima, different maxima and minimas of inversion temperature. So you can get actually this thing. If you write it, then you can get this expression. Let me write it. If 3ab p by r square t square is not negligible, then for mu Joule-Thomson coefficient to be 0, and we know Joule-Thomson coefficient is 0 at inversion temperature, then the equation becomes 1 by Cp times 2a RT minus 3ab p by r square t square minus b equal to 0. And we can write is as, this is at t equal to ti, we can write it as 2a, and since Cp cannot be 0, so RTI minus 3abp by r square ti square minus b equal to 0. And you can write equations in, if you multiply with ti square, then 2a ti by r minus 3abp r square minus b ti square equal to 0. And this can be written as ti square minus 2a, sorry, this will be r by rb plus 3abp by r square. And this has actually two maxima and a minima, so this will be like this, and this minima actually 2a by rb at this. Okay, so we can get this expression also. So this is quite also interesting. So this is a quadratic equation, you can solve it. So that's the thing. And the other solution actually get you some other thing. So this 2arb actually can we get from when this 4ac term, this t term equal to 0. Okay, so that's all. Okay. Okay, so we'll meet then next week at 6, and we'll try to solve the problems regarding assignment problems and problems regarding lecture from week 5. Okay, so till then, good night and take care. Okay.